Can I request you start at
Now?
32?
Nah. All right. Thank you guys for week 2 of the AI course. Today's all going to be about math. No computation, all intuition and just like the understanding of like what's happening with the math and like why the math is the way it is. Specifically, the math we're going to be talking about is linear algebra, calculus, statistics. Math notation is a really, really big deal because you need to be in the habit of understanding like linear algebra and like array shapes. Like we'll get into that. But having this basic understanding of how these three come together is very, very important. Before we get started, I want to talk about the homework submission. We can go over that later. A workaround that Jamal said is to download the Notion app if you guys are having trouble with access with Notion. I'm not sure if the validity of that. I use the Notion browser personally, but download the Notion app. It could help you guys get access to the Notion page. And then Google Colab Notebook. So with the Google Colab Notebook, you guys don't need to keep resubmitting it, actually. If you guys have submitted it once, that's good. But all of the code is going to exist on one notebook. Meaning if you guys just share it with me once, I could reference it constantly. This one notebook is going to be the code for all of the data processing and the machine learning. So if you guys just do it once, that's all I need. So rename the notebook to something more like realistic, like main.ipynb, instead of saying like homework1 i.ipynb. Just rename it like main, because we're gonna be using the same one. And then lecture video. Oh yeah, lecture videos are going to be posted on the. If you guys go to the homepage of the Notion, it's going to be under recordings. Right now we have last week's recording, but last week was more of like an intro. You know, we will. It's only 2 minutes. We will have the full video posted shortly, and also this week's video. So all the videos are going to be posted under recordings, and I'm going to label it by like week 1, week 2, et cetera, et cetera. So yeah, it'll be under the Discord group right there. Okay, any questions before we dive into the good stuff? Okay, cool. Yeah.
So you want to do homework first, or you want to just go?
Did anyone have trouble? I mean, I feel like the homework this week was pretty simple. Did anyone have trouble with the homework?
I did. It was hard.
No way.
I second that.
I don't know. I feel like the homework was pretty simple. It's pretty straightforward. It's learning Google Colab. You don't even need to like watch a YouTube video. If you just like look around the UI and you press print hello world, you'll figure it out. What do you guys think?
That was fine. It was like that was harder.
Yeah. I think the homework in generally for this class is going to be pretty straightforward. I want to do all the hard stuff in the group discussions. That's why. All the heavy lifting, like the heavy code, is going to be during the group discussions, and then the homework is going to be like minor, like I don't know, 6-10 lines of code. You have access? Cool. Awesome. So to get started, why math? Math is helping you understand to build better models. If you guys are actually passionate about building the raw models as opposed to just coding an existing model out, math is very important to know what's going on behind the scenes. Also to interpret the results. So I have built a lot of models and I have ran a lot of tests, and never have I ever gotten it right the first try. That's never going to happen. So understand, like, even if you print out numbers from your model, they're going to be wrong. They're going to be incorrect. So math is needed to understand what's going on. Like, why is it printing out correct? Why is it printing out but incorrect numbers? And then don't memorize equations. In the real world, you'll have access to Google, so it's like very useless to actually memorize like what an actual function is doing. Memorize the intuition, but more importantly, understanding how to read math notation, I think, is way more important than just straight memorization. So linear algebra, let's start with this. A scalar is a fancy word for a number. In computer science and machine learning world, They use the word scalar a lot. Even in like research papers and documentation, they always use the word scalar. It literally just means a number. Vector is a list, either a row or a column of a number. Basically a one-dimensional like list or an array of just numbers. Matrix is expanding this idea into 2 dimensions. So you have a row and you have your column. So a row here would be 1 and 2, and then the column would be 1, 3, and 2, 4. And the way we say it out loud, writing it, would be the dimensions of the rows and then the dimensions of the columns. So this would be a 2 by 2. In variables, it would be like m by n, where m is the number of rows and then n would be the number of columns. Here we have a purely like machine learning object. It's called a tensor. You could also call this an array. You could also call these arrays, you could also call them tensors. You could also call them vectors. It really depends. So this would be a 1D vector, this would be a 2D vector, or this would be a 1D matrix, this would be a 2D matrix, et cetera, et cetera. The vernacular changes depending on like the researcher. I just want to introduce to you guys that like they're all interchangeable, just depending on like what website or what YouTube video you use.
What would the vector as a tensor be called?
A vector as a tensor would be a 3D vector. That's like one way of writing that out.
The opposite way.
The opposite way.
So the vector referred to as a tensor. That vector.
1D tensor?
Oh, so it would be a 1D tensor.
Yeah. And like I only stress this because if you guys actually build models on your own and you guys are researching papers or even just like YouTubing stuff, you're gonna find all different wording for it, and it all means the same exact thing. And I was super confused when I first started out because I was like, dude, doesn't this mean this and doesn't that mean that? Yeah, it all means the same exact thing. So a tensor is combining basically these two into one single object. So within this tensor, it's going to be 3 dimensions. We have a row here, we have columns, and then within this bigger parentheses, we have 3 more objects inside. So the first dimension is going to be your row. Your second dimension is going to be your column. And then your third dimension is going to be how many of these mini parentheses are in here. This is kind of hard to visualize, so this is a way better example. So
That was like a 2 by 2 by 2.
it is a 1 by 2. Wait, what would it be? What would it be? That's a great question.
But there's no inside brackets.
Is it a 2 by 2 by 1?
Yes. Yes.
There's no brackets.
Good call. So this would be a lot better way of visualizing it, where imagine we just have like one big Rubik's Cube, and in that Rubik's Cube, instead of like actual plastic little thingies, we have numbers that replace them. So in this example, we have a 3D tensor or a 3D matrix, 3D array, where we have your depth, we have a height, and we have a width. And then each value here is going to correspond to a single number here. Any questions so far in just like tensor shapes and the data structures that we'll be working with?
Can you say that again? What is the dimension of that?
This is going to be 3D. The first dimension is going to be the depth. The second dimension is going to be your rows. And then the third dimension is going to be your columns.
So that one's a 3 by...
Vector that tells us the fastest way, if our ball starts here, the fastest way to get to this global minimum. Ideally a global. We don't want the ball to roll here. Sometimes it does, sometimes it doesn't. But what's the fastest way to save compute for our ball to roll from here or any arbitrary point to our global minimum? We want a minimum, not a maximum. I'll discuss that later on in like the deep learning section. But yeah. Unfortunately, we don't know what this landscape looks like. This 3D landscape looks like. We're taking a shot in the dark. And the best way to explain it is with this foggy hill analogy. Imagine I'm on top of a mountain and it's really foggy. And the mountain itself is going to be this landscape, this gradient vector. And this foggy landscape, I can't see much, but I have a flashlight. this flashlight only points maybe 10 feet. That's going to be your derivative. It's going to point into a direction, and it's going to show you how far you need to move down. With the derivative, it's the slope of a function. So how much change you need to go down this hill. So if I'm here, and I only have a flashlight that points that direction, that much, and I need to get down this hill because it's cold and it's scary, I need to go down this hill as fast as possible. A gradient is a way of telling me, even with this much flashlight space, what's the fastest way and what's the best direction to go down this hill. So that's what we need a gradient for. We're combining essentially all the partial derivatives of our function. We have a lot of partial derivatives because, as previously mentioned, we need a way to adjust all of these numbers individually. So that's why we need partial derivatives, and that's why it's in higher dimensions. Okay, this is a visualization of staying on the x point while only changing the y. So this is going to be an example of a partial derivative as our function moves across y. As you can see, the slope changes in accordance to whatever the y is, while the x is the same. This is a visualization, like I mentioned. We're not doing any of the math, screw that. Okay, chain rule. The chain rule answers the question, if I have two graphs, I have height, I have weight, and I have shoe size. Chain rule answers the question of, given a height, what's my shoe size? So we have this relay race of information of let's pass information on. And as you guys know, chain rule is like this, right? You guys are familiar with chain rule, I think?
Yeah.
All right, perfect. So this is the example that we use in school in machine learning and deep learning. The functions that we're using are way crazier than just your typical functions, and there are gonna be a lot of functions. So it'll be something like crazy long, where every function is leading to something else. Every function is going to be a relay race to the next function. And so chain rule is responsible for passing down information, but also more importantly, pointing out where in this relay race is it going wrong. And we're able to do that with calculus. Like I mentioned, calculus is the way to shift our data. So we're able to shift the data, or we're able to change the function so that let me just go back. You know what I said 5 seconds ago. This is the actual written out version of a chain rule with multivariables. As you can see, every single one of these is going to be its own individual function, and we're taking the partial derivative of something with respect to a function, and we stack that all together. And we stack it all together. Mathematically, this is what's happening. Computer science E. This is a vector. This is a vector, and this is a vector. We squish these vectors all together, and we do calculus on it, so it's a lot faster and easier. But I'm not going to go over this. This is just to show you guys. Okay, in total, calculus, the derivative is the thing that changes. The gradient is the thing that changes all the changes. And then the chain rule is the messenger. It passes down information of at this point in the warehouse, we have an error, right? But at this point, it was influenced by this point and by this machine. But then this is the error. So it goes from here to here to here. And we need a way to fix this. But we don't know if the error is this, or this, or this, or all three of them. Chain rule tells us which part is incorrect. How we change that is with derivatives. Does that make sense so far?
Yeah.
Cool. I did have to explain like I'm 5, but I do think you guys get it. The only thing I would say is in calculus, it tells the chef how to change the recipe. The gradient, the gradient is responsible for making changes one step at a time within this whole laundry list of ingredients and instructions. And then the chain rule is like, imagine I have a really burnt cookie. Who's to blame? Would it be the oven temperature? Would it be the sugar? Would it be the mixing? Who do I blame in here? Who's responsible down this chain of events to this burnt cookie? Now we need to go backwards and see who's wrong in this situation, right? Okay, statistics, where are we? All right, we're skipping statistics because I think mean and standard deviation is pretty easy. What do you guys think? We're skipping it. This is important. Okay, normalization and standardization are two ways of scaling your data. You want to scale your data because the image on the left has this red line, neon green, neon blue, and navy blue line. In this image, the neon blue is dominating over every single other variable, especially the red one. We need a way to say all of this information should be the same and we should treat it equally. And that's what normalization and standardization does, just in different methods. As you can see, the formulas are very, very similar. Just that normalization uses maximum and minimum, while standardization uses standard deviation on the bottom as our ratio to scale our data. So normalization inherently is susceptible to outliers because we're using max and min. If you have a really wide min or a really wide max, that's going to scale your data disproportionately to standard deviation. Does this make sense?
Yes.
Cool. Same process, we're basically doing the same exact thing where we're moving our data. Okay, visually, imagine we have all these data points, and we have this dot, and we have this dot, and we want to measure the distance between the two dots. The vertical distance is going to outweigh the horizontal distance, but we don't know if that information of a horizontal distance means more than the vertical distance. So we need a way to normalize or standardize this data. So that's what it looks like, right? This distance and then this distance. After we normalize it, the distances are much similar. This navy blue and this purple line are relatively similar. This is how we scale and how we do feature engineering. This is one way of doing it. It leads to faster convergence and it computes distances appropriately. Computes distance appropriately, that's what I've been going over. Faster convergence means making that ball roll down the hill faster. So linear algebra manipulates data. Calculus tells you the direction of how to move the data, and then statistics is how to interpret the data and how to feature engineer the data. All good?
Yeah.
Okay, cool.
Yeah.
Now let's do math notation. So
No.
I'm really, really big on math notation because I really want you guys to eventually build models yourself. And the only way to do that is to understand what's going on behind the scenes. This is going to be one example. This function is called, I think this is called a sigma.
Yeah.
Hey,
Yeah.
sigma, right?
Are we gonna do some math right now?
If you consider understanding this stuff math, then yes.
Oh,
So yeah, we got okay. So we have this function and we have our input. So as you guys know, this is always going to be our input, right? Of our sigma of yada yada, whatever our input data is. This means summation. This means we're going to add up a bunch of stuff. Like I mentioned to you guys as well, in machine learning, everything is vector or matrices. In this example, this is going to be a vector. So we have a vector called z, where every point in z is going to be reflective of I. I stands for index, right? So what we're doing here is we're taking an arbitrary data point in our z, we're putting it there, and then we're going to be dividing it over the summation of every single value in z, right? So all we're doing here is we're taking a vector, and the output of this vector is going to be another vector of the exact same shape, where the numbers here are going to be numbers that are scaled down because of this. In machine learning, dividing almost always means scaling something or taking a ratio of something, or like normalizing. I'm not sure if you guys have taken, I forgot what class, I think physics, but dividing by something usually almost always means by like scaling a number down, depending on whatever you're putting in the bottom.
Okay.
Yeah. So what we're doing is we're taking a, let me erase this. 7, 3, 2. We're taking our number, and it's going to be like, so e to the power of n, of e to the power of z sub I, let's just do 9, divided by e9 plus e7, dot 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 to ek, where k is the number of values or number of dimensions in this vector. So we're dividing e to the 9 divided by this, and this is going to give us a number between 0 and 1. So I think this is just an example, by the way. Let's just do this. I know there's only 3 numbers. This is 4. Doesn't matter. The output here should all equal to 1. So wait, let's do 0.6.
So it's just a series?
Kinda. You could. No, this is summation.
Oh, it's not a series.
Not a series. Not a series.
So basically, this is a way of taking every single, you have a vector and then you take every single
A series
arbitrary
can be
dimension in it
dimensions.
and then you normalize it so that you can compare it with other.
Yes, exactly. The reason we do this, in this specific function, is because we want to turn a vector of raw numbers, or called raw logits, into a vector of probabilistic outcomes. So this number is between, the output is between 0 and 1, so 0.3, 0.2, 0.1, and 0.6. These all equal to 1 if you add it up. This means you have a 30% probability of this happening. You have a 2%, 20% probability of this happening, 1% and 6%. So this number, this function, takes in raw inputs and outputs a vector of probabilities. This vector is going to be then, you can do whatever you want with it, but this is what's going on with math notation. This is how to interpret math notation. So on the bottom we have j and we have I. They pretty much mean the same thing, and we're starting at 1. So we're starting at the first value of this, and we're going all the way to the kth value, which is here. So from this number to this number, we're going to just multiply it out, or I'm sorry, add it out with e to the power of whatever the number is here. Any questions on this function in this example? E to the what?
E to the second, since the last element was 2.
E
Easy.
to the second, what do you mean?
Because
You mean-
k is like representing the number of the last element you want to go up to.
Yes.
In the vector, the last number is 2. So you, instead of adding e to the k, you would add e to the second, right?
K is going to be a number that represents the total number of values
So it's
here.
like going to infinity.
So this will actually be 4.
Yeah. Yeah.
Okay, let's go over some, so this is what it looks like. This is the same exact function. We have our inputs, our vector of raw inputs, and this could be any vector. Imagine that this vector is our features of dogs, and we do a softmax function, and then we get a vector of probabilities. Machine learning wise, we're going to say that this feature of whether it's a dog, in this example, is going to be here, which is 0.9, which is the highest. So our model predicts that this feature vector, has the highest probability of this. And this could be whatever. So this could be cat, this could be dog, frog, blah, blah, blah. And this is exactly what's happening with LLMs as well. You have a vector, like a word, I like pizza. No wait. I like pepperoni. Blank. So you have this as a vector, you have this as a vector, you have this as a vector. What's the next word in this sentence? An LLM, like ChatGPT, would take in this vector here, and it's gonna go through some LLM stuff. And at the very end, it's gonna do a softmax activation function. And we're gonna have a list of a vector of probabilities.
Yeah.
Each one represents a word, and this word is gonna be here. So now we have dog, and then this dog goes here. We do the same thing over again.
Yeah.
And so, yeah, that's it. So an LLM is literally just a autocorrect on steroids. LLMs are not taking your jobs, guys. I hate when people say that. It's not. This is all it is. It's very simple. Yeah, Cyrus.
When does it know when to stop?
When does it know when to stop is a great question.
Where did no one?
I don't know. I think that, so this is a vector, like I mentioned, there's like dog, but there's also like special things like exclamation points, or EOS, stands for end of sentence. And I'm willing to bet there's also like end, like statement, like an end statement probability. You know what I mean? I'm sure they have something like this to like actually cut off.
The highest chance of sentencing.
Exactly, yeah.
I was thinking about like GPT 3.5 and like plans like QWQ when they just came out. QWQ in its very initial stage, it wouldn't have like the thinking or reasoning tab. It would just display its reasoning and thinking, have like this neurotic way of just going on and over and over, and like recursively thinking. But sometimes it just wouldn't stop. Like I would end up having to pay extra money for a bunch of like API tokens that didn't mean anything because it just kept going on and on. And at a certain point, it just like starts switching to like Mandarin, for example. So it's like I wonder like how does an LM determine an end statement? And how does it get lost?
Well, I think they're stealing your money at that point. So, but in terms of ending a statement, I do think there is a value or a value in the vector that just cuts it off. How they actually implement it, like specifically, I'm not sure, but I'm sure there is something that's like this.
And one more.
Or maybe like the training isn't robust enough, and that's what it's at.
Yeah, exactly. Like with training too, like so the important thing about training and feature scaling is that like if you don't have high quality data, and it's crazy to say because like high quality data in terms of LLMs, they're just like sentences. So you need like really good sentences. But what constitutes as a really good sentence? How is it factually correct? You know, so all of these things get to consider when like training an LLM or ChatGPT. But yeah, are there any questions like regarding this stuff?
Pretty straightforward.
Cool. This is the function what it looks like. It's between 0 and 1. So the higher the input is, the most likely it is closer to 1. And the more negative it is, the closer it tends to be 0.
Okay.
Looks like an S. That's why it's called sigmoid or a softmax. Some math notation. You guys know these three. Transpose is capital T. Element-wise multiplication is just this circle with a dot. And if it's element-wise addition, it would be a plus, not a dot. Summation, we went over. Concat just is these hard brackets. Y and y hat, so A is going to be our actual output. Hat is our model prediction. Does that make sense?
Yeah.
Okay, cool. And then our gradient it's going to be a triangle. Or I think it's called a, you remember what it's called, Jamal?
Is it a delta?
Del F, del function. Partial derivatives is del UF over del UX. That's this part. Summation, like I mentioned, so we have I to 1 to 9. It's 1 plus 2 plus 3 all the way to 9. Transpose is, if A is this, we have a 2 by 3. A transpose is going to be a 3 by 2. So we have A, B, C, D, E, F instead of row-wise. Concatenation is, like I mentioned, hard brackets. And we're taking our A matrix, our B matrix, that have the same exact column of reference, and we're stacking them on top of each other.
Okay.
All right.
Oh, I see that one more time.
This one?
Yeah.
Yeah. So we have our A's here, so 64 and then 64, and then we have our 1, 1, and then we're stacking A on top of B. Yeah. Okay. How much are you? Okay. what's the shape of W? Given our input, where x is 32 by 128, we have our bias that's 64, and we have our output, so with this thing is a 32 by 64. What's our W? You guys are a group, you four are a group, and you three are in a group. After this is all. Oh. We're doing all. This is all group discussions, guys. So like, this is like, I know I was talking about, but this is like lock-in time. This is like focus time. So if we were to look at number 3, what's actually happening? Well, a way to visualize it in your head is by like crossing this out, and everything in this 3, this sheet of paper, this sheet of paper, and then this sheet of paper contains this 5 by 4. So if we have another dimension, like n, we have a bunch of these Rubik's Cubes. And if we look at this Rubik's Cube, and we cross this out, what are we actually looking at? We're looking at this 3D shape. And then within this 3D shape, we cross this out, we're actually looking at the actual height and width. Yeah. Does this make sense so far, guys? Perfect. Row by column.
Yeah, so it's 4 by 5.
1, 2, 3, 4. Yes. It should have been 3 by 4 by 5. Yeah. That's a good call, Professor. That is correct. That's correct. Fortunately for us, the height and the width usually they're important, but when we're dealing with images, you can honestly kind of say like height by width. Well, if we have something like this, and this is the height and width, and this is just an image, we usually just oh yeah. Code-wise, we don't really mention like 4 and the 5. We just say the last 2 dimensions of this object, right? Or we'll say we want to manipulate this dimension of the object. When we manipulate this dimension of the object, we're actually manipulating like these 2. But we'll get to that in a couple of weeks. For now, we'll stick with just understanding the basic shape of the data we'll be using. So a little game. What is the array shape of this data object? You guys can just say it out loud. What's the array shape, or how many dimensions does this data object have?
I think it's just a single.
How many dimensions? How many dimensions does this have?
Oh, only one dimension.
One dimension. What about you three?
Oh, there's rows and columns. I think it's in it.
What is it called? I can't see that. But the first one would be in being the dimension, then rows and columns.
So I'm seeing 1 or 2 as the overall vibe, I guess. Who thinks it's 1? You say it's 1? Who thinks it's 2? Okay. It is 2, because you have your height and your width. If a one-dimension object would be something like if I'm talking to you and you want to record that, and you get a signal, that signal would just be a one-dimension thing, and the numbers inside of it. So that would be an example of a one-dimensional data object. And then within here, to turn this or to extract a one-dimensional object, you could either get this or you can get this, where the row represents, I think, like a city or something like that, and then the height represents the column information, like area code, item, stuff like that. Does that make sense? Okay, cool. Oh, hey. Take a seat. Crazy question. What's the array shape of an image of Shrek in this example? 3 got 3. I'll write that. Any other? 2? Okay. For those who say 2, why 2? That's good. That's yeah. Valid.
Yeah, this has point. This has point. But we considering the
Right. Right.
The point is you're asking for the shape, right? So
The what dimen? How many dimensions? How many dimensions is it? Two, two, two. Any threes?
as a shape,
You-
it's three. It's three.
You're saying three. You're saying three.
Do you ask the dimension to create this image?
I'm sorry.
Do you ask the dimension of data to create this image or the object?
Yeah, just like the object. Like how many dimensions is this? Like so, if I were to scan this into my computer and it outputs the dimensions of the array or the matrix, what dimensions would it be? It's either 2 or 3. So this is kind of a trick question, kinda. So Jerry just answered it. Yeah. So it depends on the color, right? So a colored image is going to be 3D. A black and white image is 2D. I would have accepted both answers. I don't think that you guys would have known that. That was kind of a trick question. Sorry guys. Yeah, I tricked you guys. So we have red, green, and blue. Yeah, RGB. So you guys, it's crazy to think of an image like this really creative, artistic thing as purely numbers, but literally all an image is a matrix of numbers. The numbers range from 0 to 255, where 255 represents the most red or the most green or the most blue. 0 means nothing. Same with black. So 255 would be black. Anything between would be gray. 0 would be white. And so what you're seeing in an image is literally a 3D matrix where the colors, depending on the number, reflect or they show that color. So in the previous image, Shrek is green, so he would have a lot of like green, and then the red and the blue would be zeros. And the matrix would all be the same shape, of course, right, for this. So an image of Shrek is 3D. A black and white image would be 2D. Okay, let's check out this video. Yeah. I saw this video, I was like, yeah, this guy is killing it, dude. What is the array shape of a video? I have 4. I have 3. I have 4. Okay, 3. I heard 4 once and heard 3 the most. Yeah. So in the computer, if I were to process this video into my computer, Python it. 4, 4, 3.
I mean, the dimensions, they're not spatial, they're just arbitrary. So
I think it's three.
you would need like 1, you would need like at least 2 for pixels.
I see.
Another one for color and then another one for like sound or something.
How is the color dimension?
Is it, or maybe 3 for
Oh, sorry. Ignore the sound. Sorry, that was instead. Ignore the sound. Actually, I just wanted to play the video because it was cool. Ignore the sound. Ignore the sound. Yeah, sorry. It's 3. It's the same exact as the previous one. Oh. Yeah. So I'll ask that one in a bit. It's 3 because all we're doing is a video is literally just a stack of images next to each other. And so in the regular image, you have 3 dimensions. In the video, you'll have the number of frames times 3, right? And that's a video. And this would be the depth. This would be this dimension. So the depth would be 3, the number of images, times the number of frames. Still with 3 dimensions. Does this make sense? Okay, so that's going to be my next question. How would I make a 4D array if my object are videos? Oh, you don't have to raise your hand. You can just say whatever you want. Time. Could you elaborate?
Like moving back and forth in a
You would still be crossing in the D dimension, right? So we have depth, we have height, and we have width. Cyrus was saying if we move along the D dimension, or if we move along this dimension, we could make it 4D, but we would still be having three dimensions actually. How can we make this a fourth dimension? Or like, what can we add to this to make it a fourth dimension?
It's even hard to imagine 4 dimensions, honestly.
No, in this arbitrary example, you're kinda a different type of what? We need to add a different what?
I think just break the like sometimes maybe
I see what you mean. Like,
break the times the number
yeah, keep going. I know what you mean.
number of what? The number of the segments of video or
Yeah, that's one way. So we have D times H times width, and what he said is we can chunk D into, let's say, 8 groups. So we would have, no, wait. Yeah. We would have D over 8 by D times height times width. By dividing this by 8, and now we have 8 separate videos. Does that make sense, guys? You guys are.
so what's the point of doing
That would be like the number of videos.
This is an arbitrary example. This is an easier example than the stuff we're going to deal with. If you guys can understand this, it'll make your life a lot easier down the line. Trust me, everything I teach has a purpose. There's no fluff in this material. Like, I only want to teach you guys like specific deep learning material. So it seems arbitrary right now, but trust me, this will have a purpose once we get to like the more advanced topics down the line. But this is a good way to chunk a video where we're taking this dimension. We have like, I don't know, 8 minutes, and we want to divide each of those into 1-minute segments. So now we have a 1 minute here, 1 minute, 1 minute, 1 minute, 1 minute. And within each of these minutes has their own depth, their own height, and their own width. Yeah. Another way, the answer that I thought of was just to add another video. Like have a video of this guy, have another video of another person, have another, like, so your YouTube playlist is like a 4D array. Yeah.
It's not in the way that you would think, but because
Yeah. You got to stretch your brain out a little bit for these
It's like
exercises.
you have an individual video, but then you extrapolate that out to an extra dimension. You have a playlist of like the collection.
Exactly.
Every time you extrapolate an additional dimension, you just what am I trying to say? You're trying to
Like zoom out,
yeah.
kinda.
So
Yeah.
like the current object, as you extrapolate it out to an extra dimension, it becomes a single unit.
Yep, exactly.
It becomes a collection of individual units.
Yes. Yeah. And in that arbitrary example, like a 5D array would be a different person at that point, right? Cool.
Like a different channel, maybe.
Yeah. I see where your mind's at. Okay, this can sound really basic, but I want to talk about multiplication intuition because in math we're just taught to do things. We're not taught what they really mean. Unless you're in physics, then you can be taught what they mean. Multiplication in the terms of machine learning has a very, very deep understanding. So this is a very arbitrary example. Imagine we have 2 people talking. We have person 1 and person 2. And person 1 is telling a story to person 2. And person 2 is pretty engaged. She's like, listening very intently. So she's retaining around 80% of the information from person 1. We could actually model this process with just a basic multiplication by saying the story or the data or the input or the x times 0.8 is going to equal our output. So multiplication means how much you want to absorb something, anything, right? I know in physics it's like to scale a vector, which is exactly what we're doing geometrically, but intuition-wise, this is also what it means. So just different understandings of the same exact thing. We'll be working with vectors and matrices, but I'll abstract all of this to like regular scalars like x, 1, yeah. The next thing we're going to learn about is a dot product. So we're going to be basically, a dot product is essentially, you have a vector, you have another vector. If you want to take the dot product of these two, you're going to be taking the first value, multiplying it by the second value, which is here, and then adding, and then repeating that. So what we're doing essentially with the multiplication example that I just told you guys about is we have our input of x. We have another vector of how important these values are. And then we want to multiply that and then add them together. And the final product of that is going to be the summation or the aggregation or like the stacked info of how important this is, our data is, in this arbitrary example. What this number is our data, it's our input. So if we have MRI images, if we have words, anything that's machine learning ready, that's going to be here. The numbers here, how important this is going to dictate, this is dependent on the task we're doing. Specifically, it's dependent on calculus. And we'll discuss that in a bit as well. Are there any questions so far here? Cool. Matrix multiplication, it's the same thing as a dot product. I'm not going to go into the computation. But all we're doing is taking the first row of our first matrix, multiplying it, and then doing a dot product on the first column of the second matrix. And that number is going to be here. And then we do the same thing again here, this time for the second column, and that's there. It's the exact same thing, just in matrix form. You guys will learn this in linear algebra. It's not too complicated, I don't think, but they also don't teach you the intuition of what's really going on. There is a huge, in machine learning purposes, there's a huge thing about matrix multiplication. This is like the core engine, honestly, of why we're able to do what we do. This is our way of manipulating data and like shifting it around. And I'll discuss that in a little bit. But just the basic computation is going to be, we're doing a dot product of the row, column, and that's here, row, column, and then that's here. And then we just repeat that for the entire thing. The most important thing to note is that when you're doing matrix multiplication, the number here and the number here, so the column in the first matrix has to match the rows of the second matrix. So 2 and 2. And then the output is going to be 3 and 3, which is right here. This has to be the case. And I'll say this now. I'll give you guys not a warning, but computationally, this is so hard to wrap. All this matrix multiplication is very hard to keep track in your head. And so the biggest debugging issue that you guys will have once you guys start coding out these models is exactly this. So I really want to I really want to emphasize keeping track of the dimensions in your head. And that's why I was grilling you guys earlier about dimension shapes. Because once you guys get to coding this, making sure that you guys don't get like errors, is the source of 90% of errors, in my experience, has been this. So if we can understand this before all that, before it comes up, I think it's really important. But yeah, matrix multiplication, hint, hint, group discussion, later down the line, this is really important.
And you're saying understand or keeping track of the dimensions, like making sure that they are able to be multiplied together.
Exactly. So if we have this, right? Like, so this isn't going to work. These are just arbitrary values, but this isn't going to work because n and k aren't the same value. This has to be an n, and our output is going to be m by s. And then our m by s has to go down the line with our code to do other stuff. So keeping track of this is going to be the main, I don't say issue, but it's going to be a challenge. It's a challenge. Okay, so another intuition of matrix multiplication, because this is such a core engine of machine learning, imagine we have this matrix here, and it's a 3 by 2, and this is a 2 by 3, and so our output is a 3 by 3. So this is pretty straightforward. We're going to do matrix multiplication. I already have the answer up on the left side. I want to talk to you guys about what's really going on behind the scenes. I want to give you guys an example of what's going on behind the scenes. Imagine I have city A, city B, city C, and I have train stops D and E, and then I have city F, G, and H. The numbers here reflect here, and this matrix here reflects here. This is a 3 by 2, 3 cities, 2 train stops, 2 cities, two rows, and then 3 columns, 3 cities. So what we have is city A has 2 routes to bus stop or train station D. That's right here. City A has no stops to train stop E, and that's right here, and so forth. Train station D has 1 stop to city F, and that's right here. And so this entire network of transportation could be modeled with matrix multiplication. And when we do matrix multiplication, the output is, take a guess what, or group discussion. What does this number represent? What does this, like, what do the numbers represent on the output of our city to train stop to city data? You guys gotta discuss that or just scream it out. What do these numbers mean? The output, yeah, of course. But what do the outputs mean?
So 2 equals A, and you said 1 equals F?
So these are the cities. These are the train stops. And then each line here is representative of the number here. So if we look at this number, we are looking at city C, because this is the 3rd row. And we're looking at how many connections city C, this entire row, how many connections it has to train stop D. Has 1 connection, because it's 1 green arrow, and it has 2 connections to bus stop E, which is 2 arrows here. And then the same thing's happening here, but this time with this. So we do matrix multiplication on this, and then we get this. What do each of these individual numbers mean in terms of this?
So each row in the first matrix is a city A, B, or C. But what about each column in the second matrix? What does that mean?
Here?
Yeah. Each column.
Each column represents a city, F, G, and H. I'll give you guys a hint. These represents, I don't want to say. So we have city, city, city. We have city, city, city. And we have a train station here. Remember when I told you guys the dimensions? When we multiply the dimensions, it has to match. What are the dimensions here then?
That's 3 by 3.
I'm sorry?
Is it all city?
Here?
Yeah.
Yeah.
All city, right?
Yep. So what does that mean? What do the numbers mean then?
Destination.
So each,
What about the destination?
I think for the final 3 by 3, each individual cell represents, I think, the potential routes from one city to the other city that exist
Okay.
as you go through the train station.
Yeah.
Like that.
I don't want to say yes or no, but Cyrus?
Mine is like on the top row, it says like the city number, and it says like train station 2. It goes to the second column on the second matrix. That has like TT and then CCC on top. Goes to the second one, and then the 3rd column indicates which city will be going to as a result of going into that middle matrix.
Yeah. Your explanation was an extension of Oscar's explanation, and that's exactly right. So these, the numbers here represent the number of routes you can take from any city to any city. So I believe this is city A, B, C, F, G, H. Let's take this number, B to H. We have B. We have a purple arrow to E, and then we have 1 arrow to G. So there's only 1 route to B to G. Let's do C to H. We have C has two ways to go to E, and then 1 way from E to H. So this is 1 way, and this is 1 way. So that's 2. Yeah. So that's another way of viewing matrix multiplication. We are able to map, or I think I Oh yeah, so there's that. We're able to map input vectors into a system, and this system represents the changes that's occurring. We want to model change accurately because data in real life is never pretty. It's always going to be sporadic and crazy looking, and so we need a way to efficiently model these changes. And matrix multiplication is one of the best ways to model those changes. Another intuition. Okay, I know this is very intuition-based, but imagine we have a matrix, an arbitrary matrix of features. And each vector in this matrix is going to be a certain feature. So I'll write it out like window or door, color. So imagine if we have a matrix of houses, and within each vector, each vector is a representation, number-wise, of a feature. And we're doing matrix multiplication between this and this to get a new matrix. We're going to take this feature of a window, and then we're going to do the dot product of this, because this is a column and this is a row. So what we're doing, the output of that is going to be a rescaled version of a window, depending on what the numbers are in this column. And then we keep doing that. So we do that again for window, multiplied by that, dot product that. And then we do all that for window, and then we do for door, and then we do for color. Does that make sense so far, guys? Okay, cool. So the output of this is going to be an enhanced or a different version of the features from the original version. And like I mentioned, we have the information here. We know what this is. This is just going to be our input data. We don't know the numbers here yet. But yeah, it's calculus to get those numbers. Like I mentioned, matrix multiplication is like probably the most important basic math property in all of machine learning. We are able to scale and rearrange and manipulate data to our own, to what we want. The reason we're able to do that is because if we have something like this, and we're trying to predict whether something is a dog, a cat, or a frog, so we want the output to be three things. We want dog, cat, or frog. You're going to want an output of three things, 3 dimensions. So whatever we do here from our input data to the very end, we need to get 3. And we're able to put any number here, like computationally, as computer scientists, we can put any number here to make sure that the final output is something of m by 3 for this. So matrix multiplication is very, very, very important for a lot of reasons. Manipulate data, scale data, reshape it, project it, expand it. Also, with NVIDIA, another important thing about matrix multiplication is that we could do parallel compute. So like I mentioned, when we have our vectors and we're multiplying it and doing a dot product with the matrices, we can do that. We can do all these things at the same time with stuff like NVIDIA's GPU, which is why NVIDIA is such an important company, because the overhead of all this compute at the core of it is matrix multiplication. And we're doing that so many times. We're doing it with a bunch of numbers and huge, huge matrices that the compute is very heavy. So we need a way to do it all at the same time. And that's why companies like NVIDIA are really, really rich right now. That's the specific reason why, if you guys are ever wondering, like, what are they doing exactly to be so rich? This is an example of matrix multiplication. So as you can see, we are projecting this thingy to here, or vice versa, it doesn't matter. The reason we want to do that is because your data, the ideal data, is going to live somewhere in a higher dimension. Let's just say our data is, or the correct data is here, but our input data is like here. We need a way to move this data to here. And so we do that with matrix multiplication and linear algebra. So linear algebra is just a way to manipulate and move the data in higher dimensions. That's all it is. The direction of where we're moving the data is going to be with calculus. This is just another transformation of the data. Whatever the data looks like, we want to be able to shift it and like mess with it so that it fits what we want to get higher accuracies, to get higher predictions and stuff like that. Okay, next part. So we're done with matrix multiplication. The next part is called a convolution. A convolution is very, very, very similar to a matrix multiplication. It's just multiplying and adding. Imagine we have an input data, and it's this blue thing. And then we have another matrix, and that's the dark blue thing. And what we're doing is shimmying the dark blue from the top left, and then moving it over, and then just doing this zigzag pattern. And so what we're doing actually is scanning the image and multiplying stuff. And when we're multiplying the data, we're absorbing what's important from the neighbors. So if this stops moving, no, wait, no. Yeah, okay, so behind the scenes, this is what's doing. Imagine we have this. This is going to be the dark blue in this image. The dark blue is going to be this matrix. The original input image is going to be here. We take this, we put it to the top left, and it's going to be this red box. We do some math stuff, so we're going to be multiplying. So we have A multiplied by U, which is going to be here, and then B multiplied by V, that's here, and then we add it all together. So we're aggregating the neighbors of the data of this particular image, and we're summarizing it. Now, depending on what information is important or not, depends on this matrix. And then we shimmy that over to this green one, and we say, okay, from here, what's the important information here? And we're going to aggregate that, and then we're going to get one number, or we're going to get one scalar, or a scalar here. And we do that over and over again. We're doing this to compress the original input data. We want to compress it because in real life, input data is going to be really, really big. So normally this is going to be like, for example, if this is a 28 by 28, that's like 500 pixels. Now imagine if we have like 1,000 images. So we need a way to compress all images so that we're only receiving relevant information. And remember, when I told you guys how when we're multiplying, we're only receiving, like, we're dictating how important the information is, right? So that's what multiplying is. And we're still having that concept here. Cool. That's the thing again. Any questions on convolutions so far? Okay, cool. Okay. So I remember I talked to you guys about like signals. A convolution is also really important in signal processing. So imagine we have two signals, or I'm sorry, imagine we have one signal, and the blue is our original signal. We could perform a convolution on it, and what we're doing is instead of having like random numbers here, we're performing a convolution on a 1D vector, and the output is going to smooth or denoise the original signal. And we do that by having 1.5 by 1.5 in our vector here. And we apply that entire thing across our original signal. So the blue one, as you can see, the amplitude went down, and it's less spiky. It's also, so it's less spiky. What it does is it ignores this part. It ignores this part, and it only focuses on parts with high frequency, which is going to be in the center, and it ignores everything else. This is called smoothing or denoising, and this is just a way, both in images and also, of course, in signal processing, to manipulate data. The reverse is true for a high-pass filter. The high-pass and low-pass aren't really that important, but in this type of version of a convolution, the numbers we're using are -1 and 1 for our filter, or for this thing right here, the dark blue. And in the high-pass filter, what we're doing is we're not ignoring, but we're attenuating, we're focusing on these parts of the signal, the places with low frequency. And when the parts with low frequency, we're just going to flatten out. We don't care about them. The data means nothing to us. And we're maintaining, or we're keeping, the parts where it's sporadic. So this is important for edge detection. The edges here are going to be like here and here, for example. So we only want to focus on this part in this arbitrary example. Any questions here? Okay. This is an image. I know I talked about signals. This is an image. This is our original input. This is our output on the left side. Which has a low pass and which has a high pass filter? You guys can discuss. Okay, how about you guys? You three work in a group. You three work in a group, and then you three, and then Tony and Professor, you guys can go in this group. So the question is, given the original input, one of these has a high pass, one of these has a low pass. Which is which? Oh, really? Oh, yeah, you were there? No way. That was the day I met Jerry and Tawny. Oh my God, 3 o'clock. Really? Joining the conversation. So the question was, Jamal, given an input image, I have 2 output images. Which one has a high pass filter and which one has low pass filter? You can.
Because I was thinking about like sound, right? But now I'm confused because like I would assume like when it comes to images, I don't know. Because like I would assume like the black, like the grayish images would be like lower frequency. You know what I mean? So I would assume the high pass filter is placed on the upper image and the low pass filter is on the lower image. What was the vertical axis? Jason.
Yes.
On the image for the group, what does the vertical and horizontal axis represent? Previous slide.
What's the question?
What does the vertical axis represent and then like the horizontal axis?
The vertical is time. The horizontal is amplitude of a signal.
Okay.
One more minute. One more minute. All right. 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 What's the Shh. All right, guys. It's 3 o'clock and I'm only on linear algebra still, bro. I got so much. We have so much to go through. Oh yeah, this is probably gonna. There's gonna be probably one more presentation that's gonna be this lecture heavy, but I swear everything else is gonna be very hands-on. All right, so high or low pass for this one? What do you guys think? High or low? High. It is high. It is high. The group in the back, why high?
Because it looks like it's home.
What?
No, it is high, and the bottom,
Sure.
it's highlighting the edge. Is that what I see?
Yeah.
It's black and white, so it's edge.
Exactly. Yep, exactly. This group, why is this one low pass?
Well, because we're talking about us, right?
Yes.
Because like I think the bottom picture is low pass because like since it's blurry, it's like almost blending the colors together, so there isn't as much contrast. If that makes any sense.
That's the exact answer. Yeah. So in the first one, it is high pass. This one's high pass because we're detecting the edges. We don't care where the colors are like similar. We only care where the colors change a lot. The colors change a lot in an image on the edges, right? So this lake and the mountains, because the sky is blue and then the mountains are purple or whatever, and it goes on and on. And vice versa for the low pass one, where we don't really care where the change is happening. We just want to blur the image. And that's what's happening here. Both of these are very important ideas in machine learning because both are able to produce different images or different features of an image. So this is a high pass for vertical and for horizontal images of a particular image. This is just a version of a high pass filter. This is what the actual convolution looks like. These things are called kernels or filters. These kernels and filters are going to be this dark blue that's shifting. The output of this is going to be this white matrix here, and that's going to be like something like this, or this. So depending on the kernel, depending on the input data, depending on the output, the output depends on the kernel and what the kernel numbers are. The different kernels produces different features. These different features are going to be representing an image, for example. Maybe this feature could be representing the vertical edges of a dog, and these are the horizontal features of a dog. And you put these features together, and you're giving your machine learning enough information to accurately predict that this is a dog. Did you have a question? Yeah.
So when you say kernel, your kernel is basically a resulting vector of a high pass or a low pass into like the original data.
The opposite. A kernel is the dark blue. The dark blue. Yeah. So our input, our image is the light blue. Our kernel is the dark blue, and the output matrix is the white, or just our output in general. Yeah. And so what we want to do in machine learning in general is to create enough features, enough substantial, expressive features that our model can accurately predict what's going on. And like I mentioned, with linear algebra, this is just a way of taking the data and manipulating it and changing it so that we can get our best accuracy or best prediction. That's what linear algebra is all for machine learning. So this idea of convolution is really important because it's I forgot what it's called, but wherever the image is, right? This C, this one has one extra vector above it. When we do convolution and we do some other math stuff, our output is still going to have a upper left green in both scenarios, even if we have an extra vector on top. We'll get more into the math once we get to convolutional neural networks, but this idea is super, super powerful because what if you have an image of two dogs? One dog is here, one dog is here, and that's data in real life. So we need to have a machine learning model to, like I mentioned, be expressive enough that it could take in all these images, and it can understand that even if a dog is here, and our next image, our dog is on the lower right, it's still going to predict this is a dog and this is a dog. And the convolution is one way of doing that. But we'll get more into like the actual nitty-gritty in the deep learning section. So convolution, edge detectors. We aggregate information from our neighbors. We take in raw data like images, and we process it, and we get meaningful features. The thing that I just mentioned to you guys, where even the the dog, different dog spatial location, That's called translation invariance. Element-wise addition and multiplication of a vector, very straightforward. Given a vector or a matrix of the same exact shape, you can multiply element-wise or add element-wise. If you're doing addition, you're stacking information. You're not making it smaller, you're actually making it bigger. So then later on, that's important. Multiplication, same exact thing, but we're doing the multiplication intuition that I mentioned to you guys before. It's a one-to-one interaction, and it's only going to be local. So with matrix multiplication, we almost have a global context for it. With element-wise addition and multiplication, we only have a one-to-one interaction, so it's more local. That is kind of down the line. Okay, yeah, so how do we transition to linear algebra to calculus? Like I mentioned, we have to manipulate our data and move it in such a way that our data is able to lay on top of our model prediction. So if our images of dogs lives in this higher dimension, but our current input lives in this dimension, we want to move this to here. So we need a way to tell and to give it a direction to our model, right? And that's going to be calculus. So something like this, these numbers, like I mentioned, is going to be calculus. Moving it from here to here is also calculus. A little background. I'm not going to go over the math. That's lame. But a derivative. We have a derivative, and this is only in one dimension, or I guess 2 dimensions. And it's going to act as our compass. This is going to be our North Star. More importantly, or more specifically, whether something is positive or negative. And that's going to determine where we shift our data. And I don't think I need to go. Everyone has taken Calc 1 or has taken derivatives, right? Okay, cool, perfect. Calc 3, it's not going to be too crazy. We want to, in a vector or in a matrix, we have higher dimensions. And when we have higher dimensions, we have more variables at play. And we want to be able to dictate how one thing changes while another stays the same. So if we have a function, like a very basic function with 3 variables, and we take the partial derivative. You guys don't have to know you don't have to be in Calc 3, by the way. If we have a function with 3 variables, and we want to say how much does this move along the x-axis or the y-axis or the z-axis by itself, we take something called the partial derivative. And then we would take the partial derivative of a vector with respect to every single value.